Hi guys. In this video, I'm going to continue where I left off in my last video about buffer overflows. Last time, I introduced the concept of a buffer overflow, and I showed a very simplified example of how a buffer overflow can cause data in a program to get corrupted so that it has values that are different from what was expected. So in this video, I'm going to continue with that by showing how a buffer overflow can also change the execution of a program by causing it to execute code that's different from what was expected. And the way that works is by corrupting data on a stack frame so that when it tries to load the address of the next instruction to be executed, the address that it gets points to the code that you want it to execute instead of what it was expecting. So to see all of this in action, I've made a really simple program here just to illustrate the idea. So at the top of my program, I have several subroutines here. I've got my main, and I've got a sub1 and a sub2. And at the top here, I've got this sub0 that prints the string, "Why are you here?" Because this subroutine should never get called. There's no place in the program that calls this sub0. We can kind of confirm that here with grep. I'll say sub0 and my program stack.c. So we can see the only place this sub0 comes up in my program is up here where it's being defined here. So what I want to do is find a way to corrupt a stack frame so that we'll actually point the execution to this function instead of where it's expecting to go. So in the program here, I've got my main procedure. I declare a variable just to have some local data, and then I call my sub1 and pass some parameters. And what happens is each time there's a function call, it has to store the execution context of the current function so that it can restore all of that when it returns from the subroutine that's being called. So here I have my local variable here, and I've given it a value. Then I call this sub1. So at that point, it will create a stack frame that contains all of the data that it needs for function main, along with a return address, which is where it will resume execution of main when it comes back from sub1. So when it comes up here to sub1, it'll create a new stack frame, and it will include all of the parameters that are passed to the function and the allocate space for the local variables. And here is where the error is that makes it possible for this buffer overflow to work, because here I've declared my string data and I've told it to allocate 10 bytes for my character array data. And here I'm going to use string copy to copy the message into this data variable. But the problem is message here is just a character pointer. So we have no idea, we have no way of knowing how many characters might be in this message. And when it does this call to string copy, there's no boundary checking to make sure that message will actually fit within the 10 bytes that were allocated for it. And that's what makes it possible to into subroutine 1. It'll create a stack frame that will have all of the parameters that were passed to it. It'll allocate 10 bytes for my data here. Then it will do these operations. Then it calls another subroutine and passes some parameters. At that point, it will store the return address of where to come back to in sub1. Then it will create a new stack frame for sub2, and it'll have the parameters passed to it, and it'll allocate space for the local data. And then when it finishes, it will jump back to the return address that was specified in the stack frame here. So it resumes execution in here. Then when it finishes, it goes back to the address that it saved for a main. So we can see if I run this program here, it prints my string that I passed as a parameter. Then up here in sub2, it just calculates the sum of the three integers that were passed to it, and it prints that, and there's no problem here. So let's take a look at how the stack frame gets built so we can see how it can be exploited here. First of all, I want to take a look at I'm going to use hex dump to get a hex dump of the binary executable. So I'll say hex dump dash uppercase C, my program, and I'm going to pipe this into less so we can scroll around in it. So we write our program here in C, the compiler translates all of that into raw machine language for the computer to execute, and it saves that as a binary executable file. So when I use hex dump here, this is just a raw dump of the data that's in that file. So the first column here, these are addresses, which are just offsets from the base address allocated for the program. Then here, this is the raw hexadecimal data for each byte in the program. And then here, in this last column, if the value for these bytes falls within the ASCII range of printable characters, it will show the actual character here. And if it's outside the range of printable characters, it just shows this dot here. So we'll be able to find useful things in here. Then I also want to disassemble the file, so I'm going to use object dump. I'll say -D to tell it that I want to disassemble the entire file. Then I'll give it the name, stack, and I'll pipe it into less so I can scroll around. Here's what it looks like as a machine language program. So I'm going to come down here to the part we're interested in is to look at the executable code, which goes in the code segment here. So here it's got code for procedure main, and then it's also got code for the different subroutines. Here's sub 2 and sub 1. So here in main, I declare an integer num, and I set it to the value hex 10. We can see all that happening in here. Here's where it moves the value of 10 into a register here to store as my local data. Then it calls this subroutine 1, and it passes it 4 parameters. One is my string literal here, and then my 3 integers. We can see all that here. Here's the 3 and the 2 and the 1, and then it passes this address. This 920 address is something we want to look at here. So if I come down to here at this 920 address, here we can see my A, B, C, D, E, F, G, H. That's the address of the string literal that I'm passing to the subroutine 1 here. So to see this in action, we want to debug this at the machine language level. So I'm going to use GNU debugger. I'll say -Q so it doesn't print all of its startup messages. Then I'll give it the name of the program. So I'm going to set breakpoints in my 3 functions here. I'll set a breakpoint in main, then one in sub 1, and then one in sub 2. Break main, break sub 1, and break sub 2. Then I'll run to the first breakpoint. So here it stops in main. So I'll disassemble this. Here we can see where the instruction pointer is at this moment. Here it's just starting to set up all the data for my function call. So I'm gonna step it down to the point right before it calls subroutine 1. That's this 80F. In GNU debugger, there are 2 different commands you can use to step through machine language instructions. There's a step I and a next I. And if you use step I, that will step through each instruction. And when it comes to a function call for a library function like printf or string copy or anything else, it will step into that and it will step through the machine language instructions in those library function calls. But I don't want to do that here because those aren't relevant to what we're looking at. So instead, I'm going to use next I, which just tells it to step through function calls and stay within the procedures that I'm debugging. So I'm going to step until it comes to the call to subroutine 1, which is here at this 80F. There it is. So when I disassemble this part, it shows it's just about to make the function call to subroutine 1. So at this point, I can look at the stack. I'm going to say info register, and I want to look at the stack pointer RSP and the base pointer RBP. The stack frame for the current execution context will be bounded by these 2. The base pointer will point to the bottom of the stack, and the stack pointer will point to the top of the stack. So everything for the current execution context will be there. And I'm going to take some notes here just so we can compare it to what happens. I'll say this is in main. So I'm looking at the info for the stack pointer and the base pointer here. Now, to see what it looks like, we can examine the RAM there. You use the X for examine, and we can tell it how much. That will be in words, and it will print four columns here, where each column is 4 words. So if I want to look at 2 of these, I'll say 8 and then X for a hexadecimal format. Then I want to look at the what's pointed to by the stack pointer. So I use a $sign to tell it to go to the address that's pointed to by the stack pointer, RSP. So here is all there is to the execution context in function main. It doesn't really have very much. Here we can see it's allocated my variable here. I told it to allocate enough for one integer here and gave it this value hex 10. That's what we have here. So then from there, it's going to go into sub 1. So I'll continue. Now it's at my breakpoint in sub 2 or sub 1 here, and it shows that I've passed it this data, a message that has an address and a value, and then 3 integers. So when I disassemble sub 1 here, I can see my instruction pointer is here where it's starting to move data around to set up for the call to string copy here. So I'm going to step through the instructions until right before this call to string copy. So I want to stop at this 7BC address. Here it is. So now it shows it stopped right before the call to string copy. So again, I'm going to look at the info for those 2 registers, RSP for the stack pointer and RBP for the base pointer. So this shows the limits in RAM for the execution context of sub 1. So we can look at that here. I'm going to use X for examine. I want to look at the entire thing. Instead of looking at just the stack frame for this, I want to see it on top of the one for main. This starts at this 20 and goes up to 70. So I'm going to say 12 words. Hexadecimal format, starting at RSP. Oh, I need to go farther than that. Oh, I still need to go farther. Huh. Okay, here. I'll save this into my notes here. So here I can see at the bottom, it's still got the stack frame for main, which was saved away here. It's got this 830 and the DD50 above that. And it's still got the local variable in main that I gave this value. Then it created a new stack frame for sub 1. And it stores the parameters that are passed to it. So I've passed it a string literal and 3 integers. And because a stack is last in, first out order, it puts these on in reverse order, starting with the 3. And we can see that up here. Here's my 3, then the 2, and then the 1. And then it has this address here, this 920. That's my address here for the string literal that I passed as a parameter. So it's kind of doing this as a call by reference instead of by value. So it's passing this address here, and then below that it stored this one, this 814 address. So in function main, after the call to subroutine 1, the next instruction when it resumes processing in main is at this 814 address. So when it stores the 814 here, that's where it needs to return to. So when it exits from this subroutine, it's going to look here for the address of what to execute next. And that's a crucial piece of data because if that gets corrupted, it'll change the execution of the program. Whatever value it sees in here, it's going to move to the instruction pointer. And the value has to be within the range that was allocated for the code segment for this program, because it can't execute anything outside of that. So if the value doesn't make sense as a code segment address, it'll just raise a segmentation fault and it will exit the program. But if the value in here is a valid address within the code segment, it will just jump to that address and start executing from there. So what I want to do, I'm going to watch the string copy call here, because here I've got my parameters, I've got my address of that string literal that I passed to it. Here I've got a bunch of zeros. This is the space that was allocated for my char data here. This is my 10-byte character array. Right now there's nothing in it because it's just allocated that to use for when I do the string copy. And I stopped execution right before the string copy. So let's let it execute that next. Now that it's done the string copy, I look here and I see my data has gotten copied here. It was all zeros. Now it has these values which represent the ASCII values for the characters that I passed to it in this ABC string here. So let's look at the ASCII table here. The first one that I passed to it is a lowercase a. Here the hex value for the ASCII code for lowercase a is this 6-1. So we can see all of those here. It's got the 6-1, then the 6-2, 6-3, etc., and then 6-5, 6, 7, and 8. This represents the ASCII values for this string. And there's no problem here because it easily fits within the space that was allocated for it. But we can see that not too far away from this array is where we have the return address that it wants to return to after it exits this subroutine. And if that gets corrupted, that's where we have a problem. So what I want to do is try to find a way to overflow the buffer allocated for this string in such a way that it will put a new address in this spot. So to do that, first of all, we need to fill up all of the space from here until the point right before that address. And then we need to put new data in here that gives it a different address to return to. So let's try that. How much do I need to overflow this just enough to get it to here? So here I've got 8 characters, stopping with H. So if I want to continue I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X. If I go up to the letter X, it should fill up all of this space. So let's try that. I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X. I'm going to go ahead and quit out of here. And then I'll have to reload these. So I'll compile it again. I'm going to say -G to include the GNU debugger information. O to specify an output file. I'll call it stack. And then source file is stack.c. So now, if I run it again, this time I'm just going to put a breakpoint in sub 1. And I'll let it run to there. Then I'll disassemble sub 1. So again, I'm going to step right up to the point where it's about to execute the call to string copy. That's this 7BC address. There it is. So here it's just about to execute the call to string copy. So info registers RSP for stack pointer, RBP for base pointer. Then I want to examine the RAM there. I'll say 16 words, hexadecimal format, starting at RSP. Okay, so here we've got my parameters that I passed to it again. I've got my 3, my 2, my 1, and the address of my string. So now if I step through this, look at them again, Here I can see that the space that was allocated for this has been filled up with my string, but now it's extended all the way to here. And here we can see that my return address has already been corrupted because a C string ends with a null character, and it put that here. So that corrupted the address that it's supposed to return to. But this still isn't where we want it to go next. So if I go back to my object dump, okay, the address that I want to jump back to is my sub-0. And just to recall, this procedure never gets called anywhere in the program, and we're trying to find a way to get it to execute this. So it just prints this "why are you here" string. So anyway, the address that we want it to find for a return address is this 400750, so it will execute this function. So what we need to do now is add to our data string here just the right data to put that address in here, 1 byte at a time. So first we need the 50, and if we look at our ASCII table, the hex for 50, here it is, it's an uppercase P. So I'm going to add that to my string. Next we want it to have this 07. That's low enough that that won't be a printable character. But here we can see 07 is the bell character, which is the \A. So I can put a \A in my string here. And then if we just do that way, then the next byte will get corrupted by that null character at the end of a string. So we want to make sure that this still has the 40. And if we go back to our ASCII values here, 40 will be the @ character. So if I add that to my string, @ I'll exit out of here and out of here. So I'm going to recompile my program like this, make sure I saved it. Now if I run my stack program, it prints "why are you here?" So it showed that we successfully got into this subroutine just by corrupting the stack frame. So let's take a look at it in action and see it happen. So I'm just going to break in sub1, run to there, disassemble sub1. So now I'm going to step through the instructions till right before the string copy at 7BC. There it is. So now info register RSP RBP X 16X starting at RSP. Okay, so here we've still got, I'm going to reload this just to show it. So what it wants to do is to return to procedure main right after the call to a sub1. So that's this 400814 address. So for now we can see it's still got that address here. So if I step through my string copy now and then print it again, now it's corrupted this data and replaced it with my 400750, which is the address that's at the start of sub-0 here. So we got our address onto the stack frame just by exploiting a buffer overflow. And obviously this isn't a real world example, but I wanted to keep it simple just to get used to the idea of looking at the stack frame when it's being created and finding how you can exploit a buffer overflow to corrupt this return address. So I quit out of here. And we notice that when I run the program, it does execute the code that I wanted, printing the message, "Why are you here?" But then it ends with a segmentation fault. And the reason that happens is because I gave it a correct address that it can go to for the next instruction, but I did not build a complete stack frame that gives it everything that it needs to be able to exit from that subroutine gracefully. So in the next video, I'll go over how we can build a complete stack frame that will actually execute the code we're looking at and then still exit gracefully so that there's no error. But that's all for this one, so see you next time.